6 months ago, NASA released a set of findings from one of its ongoing lunar research programs. The data was real, the implications were significant, and then, almost immediately, the public conversation around it went quiet. No press conference, no follow-up statement, no major headlines. For a discovery tied to Earth's closest neighbour in space, a body we have studied for over a century, a world we have walked on with human boots, the silence was unusual. And once you understand what the data actually showed, the silence starts to feel like something more than just bureaucratic delay. This is the story of what NASA found beneath the surface of the Moon, why it matters more than almost anything else happening in space science right now, and why the people who know the most about it have had the least to say. To understand what was detected, you first need to understand what we thought we knew. For most of modern history, the Moon was considered geologically dead, a frozen relic, the kind of world that formed in violence, cooled quickly, and then just sat there for 4.5 billion years doing nothing of particular interest. Its craters were ancient, its surface was static, its interior was, by most scientific consensus, cold and quiet. That picture started cracking decades ago. But it fully shattered in the last few years, as a combination of reanalyzed Apollo-era data, new orbital measurements, and readings from instruments planted on the lunar surface began pointing towards something that did not fit the old model at all. The Moon, it turns out, is not as dead as we thought, not even close. When the Apollo astronauts visited the Moon between 1969 and 1972, they left behind a network of seismometers. These instruments were designed to measure moonquakes, the lunar equivalent of earthquakes, and to help scientists understand the internal structure of the Moon, the same way geologists use seismic data to map the layers inside the Earth. The Apollo seismometers were eventually switched off in 1977, largely due to budget constraints, but not before they recorded years of data that scientists are still working through today. For a long time, the interpretation of that data seemed straightforward. The Moon had a small iron core at its centre, a mantle of rock above that, and a crust on the outside. End of story. But when researchers went back to that old seismic data using modern computational tools that simply did not exist in the 1970s, they started finding things that did not fit the expected picture. Certain seismic waves were behaving strangely. They were slowing down in places they should not have slowed down. They were bending at angles that suggested the material they were passing through was different from what anyone had predicted. And in one region in particular, the signals were doing something that nobody had a clean explanation for. That region is deep. We're talking about structures hundreds of kilometers below the lunar surface, in a zone between the outer mantle and the core that geologists call the lower mantle. In the Earth, this zone is well understood. In the Moon, it had barely been studied, and what the seismic data was suggesting existed there challenged the fundamental assumptions of lunar science. The newer mission came in the form of a small but sophisticated instrument suite landed on the far side of the Moon. The far side is exactly what it sounds like. It is the hemisphere of the Moon that never faces Earth, locked in that position by the gravitational relationship between the two bodies. We have photographed it from orbit, we have mapped it in detail, but until relatively recently, we had never put a functional lander on it, with instruments capable of measuring what was happening beneath the ground. When readings from that instrument suite began coming back, scientists were looking at something that added a new dimension to what the Apollo seismometers had suggested decades earlier. The thermal measurements, the heat flow readings coming up from deep inside the Moon, were higher than models predicted in certain areas. And the magnetic signature of the subsurface rock in those same areas was unusual in a way that prompted further investigation. Heat and magnetic anomalies deep inside a world are not random curiosities. They are signatures. They are the kinds of readings you get when the material underground has been recently disturbed, or when it contains something that is still active in ways we would not expect from a cold, dead body. When NASA's scientists began putting these pieces together, what emerged was a picture of a lunar interior that retains more thermal energy than current models allow for, in regions that show signs of having been shaped by processes that should have concluded billions of years ago. The question that followed was the uncomfortable one. Why are those processes apparently still going on? There are a few possible explanations, and none of them are simple. The first involves radioactive decay. Certain heavy elements buried deep inside a planetary body can generate heat for extraordinarily long periods of time through the slow, ongoing process of radioactive decay. If the Moon's lower mantle contains higher concentrations of these elements than scientists previously estimated that could account for some of the thermal signature, it would not, however, fully explain the magnetic anomalies. Radioactive elements generating heat do not by themselves produce the kind of organized magnetic field structures that the readings were suggesting. The second possibility is more provocative. It involves the idea that the Moon's interior underwent a much more recent event than anyone expected. Not recent in human terms, but recent in geological terms. Something that may have occurred within the last few 100 million years, rather than the last few billion. A deep interior disturbance possibly connected to stresses created by tidal forces from Earth's gravity that partially reactivated processes in the lower mantle and left thermal and magnetic traces that are still detectable today. This would not be unprecedented in planetary science. Other bodies in our solar system, moons of Jupiter and Saturn in particular, are known to have interiors that remain active due to tidal heating. But those worlds orbit enormous gas giants that exert enormous tidal forces. The Moon orbits the Earth. The forces involved are smaller by orders of magnitude. If the Moon's interior is being kept partially active by tidal interaction with Earth, that suggests our models of how much energy can be transferred through gravitational interaction have been significantly off. The third explanation is the one that scientists are most reluctant to discuss publicly, not because it is impossible, but because the evidence for it is incomplete, and the implications are difficult to manage in a scientific culture that values caution above almost everything else. That explanation involves the possibility that the structures detected beneath the Moon's surface are not just the remnants of geological processes, but something that was never accounted for in our geological models at all. A layer or zone of material whose composition, density or structure does not match anything in our current catalogue of what the Moon is made of. This is where the story gets complicated, and where the silence from official channels starts to feel significant. When anomalous readings show up in planetary science, the standard process is straightforward. You publish the data, you propose hypotheses. Other researchers attempt to replicate and challenge those hypotheses. The community works toward consensus over time. This process is sometimes slow and sometimes contentious, but it generally happens in the open. What happened with these particular findings was different. The initial results were discussed at a small number of specialized conferences in sessions that were not widely publicized. The researchers involved submitted papers that moved through the peer review process, with unusual speed in some cases and unusual delay in others. And NASA's public communications team, which typically issues press releases for findings of far less significance, produced nothing. People who follow this area of research closely noticed. There are communities of amateur astronomers, retired scientists, and space enthusiasts who track every paper published on lunar science, who monitor what gets discussed at conferences, and who notice when something of apparent significance disappears into institutional quiet. Those communities began asking questions. The answers they received were either vague or absent. Now, it is important to be precise here about what the silence means and what it does not mean. It does not mean that NASA is hiding evidence of something beyond natural geological processes. The agency's reluctance to go public with incomplete findings is, in many cases, exactly the kind of responsible science communication that should be practiced. Half-understood data reported prematurely has caused enormous confusion and credibility damage to space science in the past. NASA has learned those lessons. When findings are uncertain, when models are still being built, when alternative explanations have not been fully ruled out, silence is sometimes just science doing its job quietly. But the silence does mean something. It means that what was found beneath the Moon's surface is genuinely difficult to explain with existing frameworks. It means that the researchers involved are working through possibilities that have not resolved neatly into a publishable conclusion. And it means that whatever the final explanation turns out to be, it is not trivial. You do not get this level of institutional caution about something trivial. Let's talk about what the Moon actually looks like from the inside, because that context matters for understanding why these findings are so disruptive. The Moon formed roughly 4.5 billion years ago, in the same period when the inner solar system was a chaos of collisions and heat. The most widely accepted model says the Moon was created when a body roughly the size of Mars struck the young Earth at an angle, blasting an enormous cloud of debris into orbit that eventually coalesced into the Moon we know today. This was a violent and extremely hot origin event. The early Moon was largely molten, A global magma ocean covered its surface. As it cooled, that magma ocean differentiated. Heavier materials sank toward the center, forming the core. Lighter materials rose toward the surface, forming the crust. In between, the mantle solidified into layers of rock with slightly different compositions and properties. The whole process took hundreds of millions of years, but by about 4 billion years ago the moon was largely solid, largely quiet, and largely done. That is the standard story. And for most of lunar science history, it was sufficient. It explained the craters, the ancient volcanic plains, the distribution of minerals across the surface. It explained what the Apollo seismometers found. It explained everything until the new data came in and started explaining nothing. The zone that is generating the most scientific interest sits at the boundary between the lower mantle and the outer core. In planetary science, this boundary is called the core-mantle boundary, and it is a genuinely interesting place in any world. On Earth, the core-mantle boundary is where some of the most dramatic processes in geoscience take place. It is where heat from the still hot core conducts upward into the cooler mantle, driving convection currents that ultimately power plate tectonics. It is where the interaction between liquid iron in the outer core and the solid rock of the mantle generates and maintains Earth's global magnetic field. On the Moon, this boundary was assumed to be quiet. There is no global magnetic field on the Moon today, which suggested the dynamo process at the core mantle boundary had shut down long ago. The Moon's core is small and mostly solid. There should be very little happening there. But the readings from the deep interior do not match that picture. There is more thermal activity at depth than the quiet core model predicts. And there are localized magnetic signatures in the lower mantle that suggest either that the old dynamo did not shut down as completely as assumed, or that something else is generating localized magnetic fields in ways that have not been fully characterized. Some researchers have proposed that these magnetic signatures are remnants, fossil fields frozen into rocks that cooled in the presence of an active lunar dynamo long ago, and have retained their magnetic orientation ever since. This is a known phenomenon in planetary science. Rocks can act like tapes that record the magnetic environment at the time they cooled, preserving that information for billions of years. If the Moon's lower mantle contains regions of strongly magnetized ancient rock that could explain some of what the instruments are detecting, the problem is that the thermal signature cannot be explained the same way. Fossil magnetic fields do not generate heat. Whatever is producing the elevated temperatures at depth is still active in some form. And the combination of both anomalies in the same regions of the lunar interior is harder to explain than either one alone. One direction that researchers have begun exploring involves the concept of deep lunar volcanism that is far more recent than the current model allows. Volcanic activity on the Moon was believed to have ended roughly 1 billion years ago, when the interior cooled to the point where magma could no longer form and rise to the surface. The ancient volcanic plains visible from Earth, the dark flat regions called the mare, are the frozen remnants of that earlier era of lunar volcanism. But orbital data gathered over the past 2 decades has repeatedly turned up features on the lunar surface that look suspiciously young. Regions where the surface has not been ground down by billions of years of micrometeorite impacts to the same degree as the surrounding terrain. Small formations that resemble volcanic vents, but are surrounded by material that does not look 4 billion years old. These features have been controversial. Some researchers argue they are just erosion artifacts or unusual impact structures. Others argue they are exactly what they look like, evidence of volcanic activity that continued far more recently than anyone thought, and may not be entirely finished. If deep lunar volcanism is still ongoing at some low level, driven by pockets of heat in the lower mantle that have not fully dissipated, that would connect the thermal readings to the surface anomalies and potentially explain the magnetic signatures as well. It would also mean that one of the most fundamental assumptions in planetary science, that small rocky worlds lose their internal heat and go quiet relatively quickly, is wrong. Not slightly wrong, significantly wrong. That matters for more than just the Moon. It matters for how we think about every small rocky body in the solar system. Mars, which is also believed to be geologically dead by the same models that called the Moon dead, would need to be reconsidered. Mercury, the larger asteroids. Any world that we have written off as cold and finished based on the assumption that worlds the Moon's size cool on a predictable schedule. The mission that gathered the most recent data involved an instrument package capable of measuring seismic activity with far greater sensitivity than anything the Apollo program left behind. The technology available today is simply not comparable to what existed in the early 1970s. Modern seismometers can detect ground motion at sensitivities that would have seemed almost impossibly refined to the engineers who built the Apollo instruments. What looks like a quiet world to 1970s technology might look very different to instruments built in the 2020s. And what those instruments found, in the months of data they returned before the mission entered a long analysis phase, was a world with more internal movement than expected. Moonquakes occurring at depths, and with characteristics that suggested sources deeper in the interior than the shallow quakes the Apollo instruments had primarily detected. These seismic wave patterns that gave researchers their clearest look yet at the structure of the deep lunar mantle, and those anomalous regions at depth, the zones where the waves slowed down, where the temperatures ran higher than they should, where the magnetic signatures did not match the model. The analysis phase is where things currently stand. The data is real, and it has been collected. The teams working on it are working on it seriously. The conclusions that emerge from that analysis will eventually be published, and when they are, they will likely generate significant scientific discussion. The question is what those conclusions will say. There are three broad possibilities for how this story ends, and each one is meaningful in its own way. The first is that the anomalies are ultimately explained by refinements to existing models. The Moon's interior contains slightly different proportions of radioactive elements than we estimated. The ancient dynamo shut down more gradually than assumed, leaving stronger fossil magnetic signatures. Some deep volcanic activity continued slightly longer than the current timeline suggests. In this scenario, everything fits into a revised but fundamentally familiar picture. The Moon is still basically dead, just less neatly dead than the old model said. This is the most conservative outcome, and probably the one that most working scientists would bet on. The second possibility is that the Moon's interior is genuinely more active than current science allows, and that the models need to be rebuilt from scratch. This would be a significant scientific event. It would not overturn physics or revolutionize our understanding of the universe, but it would mean that a world we have been studying intensively for over a century is still surprising us in fundamental ways. It would change how we think about planetary evolution, and it would likely intensify interest in returning humans to the Moon with instruments capable of drilling deep and measuring directly what can now only be inferred from orbital and surface readings. The third possibility is the one that lives in the space between confirmed science and unanswered questions. The one that the most careful, most rigorous, most credentialed scientists involved in this research are privately uncertain about, even if they are publicly quiet. It involves the recognition that the subsurface structures being detected have characteristics that do not cleanly resolve into any natural geological explanation currently on the table, that the data keep suggesting something whose composition or properties fall outside the known catalogue of what planets and moons are made of. Nobody who's asking to be taken seriously in planetary science is currently claiming that the Moon's interior contains anything other than rock and metal and heat. But in the private conversations that happen at the margins of conferences, in the emails exchanged between researchers who have looked at the same data and arrived at the same confused expression, there is an acknowledgement that the anomalies are real, that the standard explanations are strained, and that something unexpected is down there. That is not a statement about what that something is. It is a statement about how science works when it encounters data it does not yet have the tools to fully interpret. The history of space science is full of moments where an unexplained reading, held carefully and worked on rigorously for years, eventually resolved into a discovery that changed everything. The cosmic microwave background was initially dismissed as instrument noise. The first pulsar signal was so regular and so inexplicable that the researchers who found it half-jokingly labelled it a possible alien transmission before the natural explanation emerged. The mysterious dimming of a distant star generated years of wild speculation before a cloud of orbiting debris was identified as the likely cause. In each of those cases, the scientific community's instinct toward caution was correct. The unexplained thing turned out to be something natural, something new, something that extended our understanding of the universe without requiring a complete abandonment of everything we knew before. That is almost certainly what will happen here too. But almost certainly is not the same as certainly. And the Moon is different from distant galaxies and faraway stars in one very specific way. It is close. Close enough that humans have stood on it. Close enough that the things beneath its surface are reachable, in principle, by instruments we could build and send within a generation. Close enough that the question of what is down there is not purely abstract. When the Artemis program lands humans on the Moon's south pole, the focus will be on water ice, on resource extraction, on establishing the infrastructure for long-duration human presence beyond Earth. Those are important goals. But some of the most significant science that future lunar explorers could do would involve drilling down, getting instruments below the surface, closing the distance between the readings we can take from orbit and from the surface and the deep structures those readings are pointing toward. The researchers working on the subsurface anomaly data have been clear about one thing in the limited public statements they have made. The best way to resolve the questions the data raises is more data. Data from more sensitive instruments, data from different locations across the lunar surface, and eventually, data from instruments placed much deeper than anything currently in operation. That kind of data collection takes time and money and mission priority. The lunar science community has been making the case for subsurface investigation for years, and the recent findings have given that case new urgency. Whether that urgency translates into the kind of dedicated mission that could settle these questions remains to be seen. In the meantime, the data that already exists continues to be analysed. Papers continue to move through review, and the questions that started this story about what is generating heat at depth, about what is producing those magnetic anomalies, about what the seismic signals are travelling through when they slow down in ways that do not match the model, remain open. The Moon has been Earth's companion for 4.5 billion years. We have watched it from the ground for all of recorded human history. We have sent machines to orbit it, robots to land on it, and 12 human beings to walk on its surface. We have brought back hundreds of kilograms of its rock and analysed every grain under every instrument we could point at them. And yet the Moon is apparently not finished surprising us. 6 months of institutional quiet is not forever. At some point, the analysis will be complete enough that the findings have to be shared. At some point, the papers will be published, the press conferences will happen, and whatever is beneath the surface of the Moon will have a name and a description, and a place in the scientific literature. When that moment comes, it will either confirm that the models were close and just needed adjustment, or it will force a reckoning with the fact that our nearest neighbour in space has been holding something back. Something in the deep dark beneath the dust and the craters and the ancient frozen plains. Something that 40,000 hours of Apollo data and 50 years of orbital study and all of the accumulated knowledge of modern planetary science did not fully anticipate. Either way, it will be worth knowing. The silence never lasts forever. The Moon has been there since before the first fish crawled out of the ocean onto land. It has seen everything this planet has become. Whatever is down there has been waiting far longer than we have been asking the question. We are getting closer to an answer, and when it comes, nothing about the way we think about our solar system will be quite the same as it was before. So let's talk about what we actually know about the Moon's interior, piece by piece, before we get into the more contested territory. Because there is a foundational layer of science here that is not in dispute, that is genuinely remarkable on its own terms, and that most people have never heard explained in a way that makes the strangeness of it land. The Moon is, by any reasonable measure, enormous relative to the planet it orbits. Most moons in our solar system are tiny compared to their parent planets. The relationship between Earth and the Moon is unusual. The Moon is more than a quarter of Earth's diameter. If you were looking at the Earth-Moon system from far enough away, you might reasonably classify it as a double planet rather than a planet with a satellite. That size relationship matters for the interior because it means the Moon retained a great deal of heat from its formation. More than you would expect from something most people still picture as a cold, grey, dead rock. When the Moon was fully molten, that global ocean of magma was hundreds of kilometres deep. The heat stored in that early molten state was staggering, and heat does not disappear instantaneously. It moves slowly through rock. It radiates out into space over timescales that are hard for human intuition to fully grasp. We're talking about a cooling process that unfolds over billions of years, not thousands or millions. The question was never whether the Moon retained some of that primordial heat. The question was how much. For most of lunar science history, the answer seemed to be not much. The Moon is small compared to Earth. Small things cool faster than large things, all else being equal. And the geological evidence at the surface, the ancient craters, the billion-year-old volcanic plains, the lack of anything resembling active tectonics, all of it pointed toward a world that had given up most of its internal energy a very long time ago. That interpretation was reasonable, based on the available evidence. It was also, as it turns out, missing something. Here is a detail about the Apollo seismometers that is rarely mentioned outside of technical literature, and it is genuinely important for understanding why those instruments could only take us so far. The seismometers left on the moon by the Apollo astronauts were extraordinary achievements for their time. They were precise, they were durable, and they worked for years in an environment that is simultaneously baking hot and freezing cold within the same day-night cycle. But they were installed on the surface, in a relatively small area of the lunar near side, clustered within a geographic region that represents a tiny fraction of the moon's total surface area. Seismic data is directional, where your detectors are positioned relative to the sources of seismic activity and relative to the structures through which seismic waves travel, determines what you can resolve and what you cannot. A network of 4 to 5 seismometers, all in the same hemisphere, within a relatively narrow band of latitude, cannot build a 3-dimensional picture of a planetary interior with anything like the precision that a more distributed network would allow. The Apollo array was the scientific equivalent of trying to understand the entire ocean using 5 listening devices all placed along a single stretch of coastline. This is not a criticism of the Apollo scientists. What they did with those instruments was remarkable. They extracted far more information from that limited network than anyone had a right to expect. But it does explain why the picture they built of the lunar interior was necessarily incomplete, and it explains why, when modern researchers go back to that old data with new computational methods, they keep finding things in it that were either invisible or ambiguous at the time. The new mission that returned data within the last few years benefited from something the Apollo program never had: placement on the far side. That matters enormously. The far side of the moon is geologically different from the near side in ways that scientists still do not fully understand. The crust is thicker on the far side. The distribution of volcanic plains is dramatically different. There are ancient impact basins on the far side that are among the largest in the solar system, enormous scars that penetrated deep into the lunar crust when they formed billions of years ago. Having a seismometer on the far side means that seismic waves from deep interior sources have to travel through the full body of the moon to reach it. The way those waves change as they travel through different materials tells scientists something fundamentally different from what the Apollo instruments sitting clustered on the near side could ever have revealed. It is the difference between listening to an echo in a small room and listening to the same sound after it's travelled through the entire building. What the far side readings showed, combined with what modern analysis has pulled out of the Apollo archive, is that the moon's interior has structure that the standard model does not adequately predict. Not in a minor way that might be attributed to measurement error, in a way that has been checked and rechecked by multiple groups working with the same underlying data. The deepest anomaly sits in the lower mantle, as I described earlier, but there is a second zone of interest that I have not yet mentioned, and it is located much closer to the surface, relatively speaking. About 200 to 300 kilometers down rather than the deeper 1,000 kilometer plus range of the primary anomaly. This shallower zone shows its own pattern of seismic irregularity, one that seems to correlate with the surface regions where the suspicious, young-looking geological features have been observed. The coincidence of those two things, the seismic irregularity at depth and the potentially young surface features above those same regions, is what pushed this from interesting to genuinely difficult to set aside. Coincidences happen in science. But when a deep interior anomaly aligns geographically with surface features that suggest recent geological activity, in not one location but several, that is not the kind of coincidence that gets dismissed easily. I want to spend some time on the young surface features, because they deserve their own careful discussion, and they have been the subject of significant scientific debate for reasons that illuminate a lot about how planetary science works. The features in question are scattered across several different regions of the lunar surface. They have been identified through a combination of orbital photography, thermal mapping, and what is called radar sounding, a technique in which radar pulses are bounced off the surface and the return signals analysed to reveal the structure of the shallow subsurface. The features range in size from relatively small, a few kilometers across, to quite large, spanning dozens of kilometers. What makes them suspicious from a geological standpoint is the degree to which they lack the accumulated damage that billions of years of micrometeorite bombardment should produce. Every surface in the inner solar system is constantly being struck by tiny particles, grains of sand and smaller, moving at tens of kilometers per second. Over time, this process grinds down surface rocks into fine powder, filling in small craters and softening all the topographic features. The older a surface is, the more thoroughly it has been processed by this bombardment. It becomes uniformly smoothed and powdery at the microscale. The suspicious features on the Moon have not been processed to the same degree. Their surfaces look geologically younger in the statistical sense that this kind of analysis enables. Not young by human standards, not young even by historical standards, young in the language of planetary timescales, where hundreds of millions of years is a recent event, but younger than 4 billion years old, which is how old they should be if the current model of lunar geological history is correct. The standard objection to this interpretation is that regional variations in surface composition can mimic the appearance of youth. Some minerals reflect radar and thermal energy differently than others. A patch of unusually hard rock surrounded by the typical lunar regolith might look statistically young in certain measurements without actually being young. This is a legitimate scientific concern, and it is why the young feature interpretation has remained contested. But the objection has a limit. When you stack the radar evidence with the thermal evidence with the mineralogical signatures from orbital spectrometers with the seismic anomalies in the same regions, the coincidence argument becomes harder to sustain. You need multiple independent lines of evidence to all be independently misleading at the same time, all in the same geographic areas. That is a considerable amount of coincidence to swallow. The volcanic interpretation of these features, which holds that they are the remnants of eruptions that occurred in the last several 100 million years, rather than several billion years ago, has been gaining ground slowly but steadily in the research literature. It has not yet become consensus. The debate is ongoing. But the researchers who have examined the full body of evidence most carefully tend to land somewhere between cautious support and genuine uncertainty, which is different from dismissal. If late-stage lunar volcanism is real, the mechanism driving it becomes the central question. Where is the heat coming from? What process is still generating enough thermal energy to melt rock at the depth required to produce magma, in a world that should have cooled past that point long ago? This is where the radioactive element hypothesis comes back into the picture, and where it gets more interesting than it sounds at first. Certain elements in a planet's interior, the ones most relevant are uranium, thorium, and a particular form of potassium, are unstable in the sense that their atomic nuclei decay over time, releasing energy in the form of heat as they do. This process is slow, almost incomprehensibly slow by human standards, but it operates continuously regardless of whether the surrounding rock is hot or cold. It does not stop. It does not run out of fuel on any timescale relevant to planetary evolution over a few billion years. On Earth, radioactive decay is a significant contributor to the planet's internal heat budget. It is not the only source, and probably not even the primary source, but it keeps the Earth's interior meaningfully warmer than it would otherwise be. For the Moon, the question is how much of these heat-producing elements ended up in the interior versus the crust, and in what concentrations. The early differentiation of the Moon's interior, when the magma ocean was solidifying, distributed these elements in ways that are partially understood and partially not. Heavy elements tend to sink toward the core, but radioactive elements are chemically complex, and the way they partition between different mineral phases during cooling is not always intuitive. There is a real possibility that certain regions of the lunar lower mantle ended up with higher concentrations of heat-producing elements than the current models assume. What makes this particularly interesting from the standpoint of the anomalies is that radioactive heating is not uniform. If pockets or zones within the deep mantle contain elevated concentrations of these elements, you would expect to see thermal hotspots rather than a uniform elevation of temperature across the entire interior. That would produce exactly the kind of localized anomaly that the measurements seem to be showing. A group of researchers published a paper in the last 2 years proposing what they called a thermally heterogeneous lower mantle model for the Moon. The core idea was that the differentiation process did not produce a uniform distribution of heat-producing elements in the mantle, and that the zones of elevated temperature visible in the data correspond to regions where those elements concentrated during the original cooling of the magma ocean. The model was elegant and it matched several features of the available data reasonably well. It did not, however, fully account for the magnetic signatures in those same regions. The magnetic anomalies require something beyond just heat, and this is the part of the story where the scientific conversation becomes most strained. The Moon's global magnetic field died somewhere between 3 and 4 billion years ago, when the core cooled enough that the dynamo process that generated it could no longer sustain itself. After that, the Moon essentially became magnetically blank at the global scale. It has no magnetosphere. The solar wind strikes its surface directly, but the Moon is not magnetically blank at the local scale. The lunar surface has scattered regions of anomalously strong magnetism, sometimes referred to as lunar magnetic anomalies or lunar crustal magnetic fields, and scientists have been puzzling over their origin for decades. Some of them correlate with ancient impact basins, which makes a certain amount of sense if the impacts occurred while the global field was still active and effectively stamped the magnetic orientation of that field into rocks that cooled in its presence. But some of the magnetic anomalies do not have obvious connections to impact basins. They are just there, islands of local magnetism in a globally demagnetized world, and their origins are not well explained by any single mechanism. The deep magnetic signals detected by the recent mission instruments are different from the surface magnetic anomalies. They are coming from greater depth. They are more diffuse, and they appear to correlate with temperature, being stronger in the same regions where the thermal readings are elevated. That correlation is the piece that conventional models have the most difficulty with. If ancient magnetized rock in the lower mantle is responsible for the signal, you would expect the magnetic orientation to reflect the direction of the ancient global field that magnetized it. But the signal does not show a consistent orientation of the kind you would expect from a frozen snapshot of a past global field. It shows something more complex, more variable, more localized in its structure. The most cautious interpretation is that the lower mantle in these regions contains a mixture of differently magnetized rock units, each reflecting the local magnetic environment at the time they cooled, and that the overall signal is the superposition of many such units. This is plausible. It is not impossible, but it requires the coincidence of multiple differently magnetized units concentrating preferentially in the same regions as the thermal anomalies, and the statistical case for that being coincidence weakens the more locations are identified with both features. The alternative interpretation, the one that is harder to say out loud without sounding like you're reaching for something extraordinary, is that whatever is generating the thermal excess in those regions is also producing its own magnetic effect. That there is an active process of some kind in the deep lunar interior, not just the passive decay of ancient minerals and the lingering warmth of long-spent radioactivity, but something that is still doing something. The data does not prove that. I want to be very clear about that. The data suggests it as a possibility that has not been ruled out. There is a difference between those two things, and in science, that difference is everything. But here is the thing about the Moon that makes this conversation feel different from similar conversations about distant and inaccessible worlds. We can check. Not tomorrow, not easily, but in principle, and within a foreseeable human timeline, we can get instruments to those anomalous regions. We can drill. We can measure directly. We can close the loop between the indirect orbital and surface signals and the actual material those signals are coming from. That is an extraordinary position to be in scientifically. Most of the great unresolved questions in planetary science involve worlds that are difficult to reach, or conditions that are impossible to sample directly. The internal structure of gas giants, the chemistry of the deep ocean on a moon billions of kilometers away, the composition of the cores of rocky planets that we can only observe from the surface. In those cases, we are working from indirect evidence indefinitely, with no realistic prospect of direct confirmation in any near-term future. The Moon is different. It is close. It is reachable. The deep anomalies are not reachable by anything we currently have on its surface, but they are reachable in principle, and the technology for deep drilling in a low-gravity environment is not science fiction. It is engineering that has not yet been applied to this problem. There is a longer history here worth understanding, one that most casual observers of space science do not know, because it puts the current situation in a context that changes how it reads. In the immediate aftermath of the Apollo program, when scientists first had lunar samples in their hands and the seismometer data was still coming in, there was a period of extraordinary scientific optimism. The Moon was going to be understood. Completely. Systematically. The questions about its origin, its interior, its history, all of it was going to be settled within a generation. The scientific community had the samples, they had the data. They had the instruments, and they had the extraordinary momentum of the space age behind them. That optimism, as it turned out, was premature. The first surprise came from the samples themselves. The rocks the Apollo astronauts brought back were older than anyone had expected. Not just old, but different in their chemistry, in ways that the early models of lunar formation did not predict well. The distribution of certain elements between the lunar crust and Earth's crust suggested the early moon went through a more violent and complicated history than the standard models allowed. Researchers argued about this for decades. Some of those arguments are still ongoing. The second surprise came from re-examination of the seismometer data in the 1980s and 1990s. Researchers using analysis techniques not available in the 1970s found that the deep lunar interior was behaving in ways that the first round of interpretation had smoothed over. There were hints of structures at depth that did not fit the simple layered model. Not dramatic hints, not enough to overturn anything decisively, but enough to leave a persistent unease in the field that the moon was not fully understood. The third surprise was the water. For decades, the moon was described in textbooks and classrooms as bone dry, not just lacking liquid water, but lacking any water in any form. Dry to the molecular level, more completely desiccated than any desert on Earth, because of the hard vacuum of its surface and the billions of years of solar radiation baking every volatilized molecule away. The scientific consensus on this was firm and repeated and taught to generations of students as settled fact. It was wrong. The discovery of water ice in permanently shadowed craters near the lunar poles began as tentative and contested, and became, over the course of roughly 2 decades of accumulating evidence, undeniable. There is water on the moon, meaningful quantities of it, trapped in the cold darkness of craters where sunlight has not reached in billions of years. The scientific community had to revise a piece of knowledge that had been held with complete confidence for the entirety of the space age. That revision matters not because water ice at the poles is directly related to the deep subsurface anomalies, but because it illustrates something important about the state of lunar science. The moon has surprised us repeatedly, not at the margins, at the center of what we thought we understood. Every time the scientific community has declared a chapter of lunar knowledge closed, subsequent data has reopened it. That pattern does not prove the deep anomalies are something extraordinary, but it does mean that the instinct to dismiss them, to assume they will resolve neatly into an expanded version of the existing model, is an instinct with a poor track record. Now, I have been careful so far to stay within the territory of what the data shows and what researchers are actively debating. What I want to do now is widen the frame a little, because the implications of each of the possible explanations for these anomalies extend well beyond lunar science itself, and those implications deserve to be understood clearly. Start with the most conservative possibility. The moon's interior contains more heat-producing radioactive elements than estimated distributed unevenly, producing localized thermal anomalies. The magnetic signatures are explained by heterogeneous ancient magnetization of the lower mantle. The young-looking surface features are explained by late-stage volcanism driven by those thermal anomalies, extending the moon's volcanic history by perhaps 500 million years beyond the current model. Even this most conservative outcome has cascading consequences for how we think about planetary evolution. The models that predicted the moon should be cold and dead by now are the same models we apply to Mars, to Mercury, to the rocky bodies scattered throughout the asteroid belt. If those models are systematically underestimating the contribution of radioactive heating to small rocky worlds, every prediction we have made about the geological state of every such body in the solar system is off to some degree. Mars, for example, is currently regarded as essentially geologically dead. Its last significant volcanic activity is believed to have concluded within the last 100 million years or so, which is recent on planetary timescales, but still definitively in the past. There have been persistent hints in Martian data that some low-level geological activity might still be occurring. The InSight mission, which operated on the Martian surface for a few years and returned its own seismic data, found evidence of a Martian interior that was more complex and more active than the simplest models predicted. If the revised understanding of the moon says that small rocky worlds cool more slowly than we thought, Mars becomes a candidate for re-examination as well. Mercury is another case. Mercury has a magnetic field, which was one of the great surprises of early planetary exploration. A world that small, that old, that apparently simple in its geology should not have a functioning magnetic dynamo, and yet it does. The current explanation involves Mercury's unusually large iron core relative to its total size, which allows the dynamo to persist even in a body that should have cooled beyond that capacity. If we are systematically underestimating internal heat in small rocky worlds, Mercury's magnetic field becomes less of an anomaly and more of a data point in a larger pattern. The implications get more interesting when you extend them beyond our solar system into the expanding catalogue of rocky planets we have detected orbiting other stars. Planetary scientists use our own solar system as a template for understanding rocky planets in other systems. When we find a rocky planet orbiting another star at the right distance to potentially support liquid water, we ask whether that planet might be geologically active, whether it might have a magnetic field that could protect an atmosphere from stellar radiation, whether its volcanic history might have driven the kind of carbon cycling that on Earth has helped maintain a relatively stable climate over billions of years. All of those questions depend on models of how rocky planets evolve over time. If those models need significant revision because the Moon, our most intensively studied nearby body, turns out to have retained substantially more internal activity than they predict, then our assessments of habitability across the galaxy need revision as well. Not dramatically, not in a way that overturns the basic physics, but in the specific quantitative estimates that determine whether a given world falls on the habitable side or the barren side of our projections. That is genuinely significant consequence of what sounds like a narrow technical question about the temperature of rock 1,000 kilometers below the Moon's surface. The second broad possibility, that the Moon's interior is genuinely more active than any current model allows, and that the models need to be rebuilt from scratch, carries all of the above consequences and adds more. A Moon with an interior that cannot be explained by existing planetary science frameworks would be a major scientific event. It would not be a crisis for physics. The underlying physical and chemical processes at work are still within the domain of the known. But it would be a crisis for the specific quantitative models that planetary scientists rely on for everything from understanding how the solar system formed to assessing the likelihood of life elsewhere. Scientific crises of this kind are not catastrophes, they are opportunities. The history of science is full of moments where a model that had become too comfortable had to be broken open and rebuilt, and where the rebuilt version was more powerful and more accurate than what it replaced. The Copernican revolution was a crisis for geocentric astronomy. The discovery of radioactivity was a crisis for the 19th century geological models that relied on purely mechanical cooling timescales for the Earth. In both cases, the crisis was generative. It produced better science. But those crises were also painful and slow and contentious. They involved the scientific community having to accept that knowledge it held with confidence was substantially wrong. That process takes time and produces resistance, which is part of why, when findings like the lunar subsurface anomalies emerge, the institutional response tends toward caution and quiet rather than announcement and excitement. NASA has been through moments where premature public excitement about scientific findings turned into embarrassment and eroded credibility. The Mars meteorite affair in the 1990s, when a paper was published suggesting that a rock from Mars might contain microscopic evidence of ancient Martian life, generated enormous public excitement and enormous subsequent scientific skepticism, and the net effect on the relationship between the agency's scientific claims and public trust was not positive. The Mars meteorite was a legitimate scientific paper with legitimate evidence that simply did not hold up to the scrutiny it received after going public. The science was careful. The communication of it was not. That experience left a mark. NASA's scientific communication apparatus and the broader culture of how major space science findings are handled from data to press release shifted toward a much more conservative posture afterward. Multiple independent confirmations, thorough review, explicit acknowledgement of alternative explanations before any public announcement. These are not bad practices. They're good science. But they produce the exact kind of institutional silence we are seeing around the lunar subsurface findings. The practical consequence of that silence is that the public conversation about what the data shows has largely been carried by people who are not the researchers themselves. Amateur astronomers, science bloggers, journalists who cover space science without specialized expertise in planetary geophysics. This is not a criticism of those people. They are doing what they do in the absence of official communication, but it means that the public understanding of what was found is filtered through multiple layers of interpretation before it reaches most people, and the filtering is not always accurate. Some of the coverage has been responsible and careful, and has conveyed the genuine scientific uncertainty appropriately. Some of it has not. Some of it has leapt directly from anomalous subsurface readings to conclusions about artificial structures and extraterrestrial origin, which is understandable as a human response to mysterious data, but is not supported by what the evidence actually shows. The researchers who produced the original findings have been largely unable to publicly correct those misinterpretations, because correcting them publicly would require discussing findings they have not yet published in their complete form. It is a frustrating situation from almost every perspective. The scientists want to do their science and publish their results in the proper venue, with the appropriate caveats and explanations, and then let the community evaluate and challenge the conclusions. The public wants to know what was found and what it means. And in the gap between those two needs, a lot of noise gets generated. What I am trying to do here, and what this entire story requires, is to hold that tension without collapsing it. Not to pretend the anomalies are more dramatic than the evidence supports, because that would be dishonest, and not to dismiss their significance, because their significance, within the proper scientific framing, is genuinely substantial. Let me take a step back and talk about something that might seem tangential, but is actually central to the deeper meaning of this story. Why the moon matters to us in a way that goes beyond pure science. The anomalous region in the deep lunar interior shows wave speeds that are inconsistent with the surrounding mantle in both the primary and secondary wave channels. The primary wave velocity is lower than expected. The secondary wave velocity shows a different pattern of deviation. The ratio between the two velocities is in a range that does not correspond cleanly to any single known mantle, mineral or mineral assemblage. This is the specific technical problem. It is not that the waves are slow exactly. It is that the relationship between the two types of wave speeds points towards something whose mechanical properties are unusual in a way that is difficult to attribute to any single known cause. One candidate explanation is partial melt. If a region of rock contains some fraction of molten material that changes the wave speeds in a specific way, molten rock has very different mechanical properties from solid rock, and its presence in a solid matrix changes how seismic waves propagate. The secondary wave in particular is very sensitive to the presence of melt, because secondary waves cannot propagate through liquid at all, and are strongly attenuated even by small fractions of liquid in an otherwise solid matrix. The secondary wave data from the anomalous region is consistent with partial melt, but the primary wave data is not fully consistent with the amount of melt that would be required to explain the secondary wave behavior. The two datasets constrain the solution differently, and the intersection of those constraints does not land cleanly on partial melt as a complete explanation. There are ways to make partial melt work as an explanation if you allow for the geometry of the melt distribution to be unusual, if the melt is concentrated in thin films along grain boundaries rather than in larger pockets, or if the composition of the melt is atypical in ways that change its mechanical properties. These are not unreasonable assumptions, but they are additional assumptions, and each additional assumption reduces the parsimony of the explanation. The other candidate explanations involve unusual solid phases. There are high-pressure mineral phases that can form in planetary interiors under the right conditions of temperature and pressure and bulk composition. Some of these phases have mechanical properties that are different from the common low-pressure forms of the same minerals. If the lunar interior reached the right conditions at some point in its history, unusual mineral phases could have stabilized and persisted. The challenge with this explanation is that the pressure in the lunar interior, while substantial, is lower than in Earth's mantle, and the high-pressure phases that are well characterized tend to form at pressures higher than what the lunar interior can produce. There are some candidate phases that might be relevant at lunar interior pressures, but they are not well characterized in terms of their seismic properties, which means they cannot be ruled out, but they also cannot be confirmed. This is the state of the field. Multiple possible explanations. None of them fully consistent with all of the data. None of them clearly ruled out. The uncertainty is irreducible given the current dataset, and extending the dataset requires either new seismic instrumentation on the lunar surface or a sample return mission capable of reaching the deep interior, which is not technically feasible in the near term. What makes this scientifically interesting beyond the immediate puzzle is what it implies about the thermal and compositional history of the Moon. The Moon formed approximately 4.5 billion years ago, almost certainly as a result of a giant impact between the early Earth and a Mars-sized body. The debris from that impact coalesced to form the Moon, and the early Moon was largely or completely molten, a magma ocean that then cooled and differentiated over hundreds of millions of years. The current interior of the Moon is the record of that cooling and differentiation process. The distribution of elements, the mineralogy of different depth zones, the presence or absence of residual heat, all of these things encode information about what happened in the first billion years of lunar history. If the deep interior contains something anomalous, something that does not fit the standard model of how a moon-sized body differentiates and cools, that carries implications for our understanding of planetary formation processes more generally. The Moon is, in one sense, the best-studied example of a small rocky body that formed through giant impact. We have samples from it. We have seismic data from it. We have orbital measurements of its gravity field and its magnetic field and its surface composition. No other body of its type has been studied in this much detail. What we learn about the Moon's interior is therefore not only information about the Moon, it is information about a class of objects and a class of processes that shaped the early solar system. That is the scientific stakes of the anomaly. Not just what is down there, but what it means for how planetary bodies form and evolve. And that question has implications that extend to every rocky planet, including Earth. I want to return now to the thermal anomaly specifically, because the temperature data is in some ways the most puzzling of the observations, and it connects to a question that has been unresolved in lunar science for decades. The Moon was expected to be cold. Not cold by human standards, but geologically cold, meaning that most of the heat from its formation and early radioactive decay should have been lost to space over 4.5 billion years, leaving an interior that is largely inert, not generating significant heat, not convecting, not producing volcanism, a dead rock. The evidence that this picture is incomplete goes back further than the current anomaly. There are regions on the lunar surface where thermal infrared measurements from orbit show elevated temperatures that do not match the expected pattern. These hotspots were first identified decades ago and have been studied periodically since, but they have never been fully explained. The consensus view has been that they represent concentrations of radioactive elements in the crust that generate heat locally, a known phenomenon related to the distribution of a particular geochemical component that lunar scientists call creep, for potassium, rare earth elements, and phosphorus. Creep is interesting because it represents the last dregs of the lunar magma ocean. As the magma ocean cooled, minerals crystallized out and sank or floated depending on their density, and the incompatible elements, the ones that do not fit easily into the crystal structure of common minerals, got concentrated into the remaining melt. This residual melt was rich in radioactive elements like uranium and thorium and potassium, and when it finally solidified, it formed a layer that is still generating heat through radioactive decay today. That layer is thought to be concentrated in a particular region of the near side of the Moon, beneath a large volcanic province that erupted extensively in the first 2 billion years of lunar history. The thermal anomalies at the surface have largely been attributed to creep concentrations in this region, but the deep interior thermal anomaly is different from the surface hotspots in ways that make the simple creep explanation incomplete. The depth is wrong. The location is not perfectly aligned with the known creep distribution, and the magnitude of the thermal signature, when corrected for the depth from which it must originate, implies a heat source that is difficult to account for purely through radioactive decay of known element concentrations. This is where the deep interior story becomes genuinely novel, rather than just an extension of known science. The surface hotspots fit within the existing framework with some adjustments. The deep anomaly fits less cleanly, and the combination of thermal, magnetic, and seismic signatures in the same region of the interior suggests that whatever is producing the anomaly is producing multiple distinct effects, which is harder to explain with simple hypotheses than a single unexplained measurement would be. I've been careful throughout this account to avoid suggesting that the anomaly implies anything exotic. The history of science is full of anomalies that were eventually explained by mundane mechanisms that were simply not well understood at the time. The anomaly in the deep lunar interior is very likely to turn out to have a perfectly ordinary geophysical explanation that will seem obvious in retrospect. That is the most probable outcome. But I also think it is worth saying plainly that the anomaly has not yet been explained, that serious people have tried seriously to explain it, and that the explanation remains incomplete. That is a real state of affairs in real science. It is not a mystery in the sensational sense. It is a mystery in the technical sense, a defined gap between observations and explanations that has not yet been closed. The gap will be closed, eventually. New data will come, either from future seismic networks on the lunar surface, or from sample analysis, or from improved orbital measurements, or from theoretical advances in understanding planetary interiors. Science closes gaps. It does not always close them quickly, and it does not always close them in the way anyone expected, but it closes them. What I find worth preserving about this moment is the texture of the uncertainty, the specificity of what is known and what is not, the way that real scientific unknowns are not like fictional mysteries, with hidden clues and a single correct answer waiting to be deduced. They are more like puzzles where the pieces are still being made, where the act of investigation changes what questions are even askable, where the solution, when it comes, may not feel like a solution at all, but like a deeper problem more clearly stated. That is what is happening in lunar science right now, not the discovery of something, not yet, but the refinement of an absence, the sharpening of a question, the slow accumulation of constraint around a thing that does not yet have a name. And that is interesting. Not because the moon is mysterious in a romantic sense, though perhaps it is, but because the natural world is genuinely complicated, and the process of finding that out, one careful measurement at a time, is one of the most human things we do. The anomalous zone in the lunar lower mantle shows seismic wave speeds that are lower than predicted for standard lower mantle rock at the temperatures and pressures involved. Slower seismic velocities can mean several things. They can mean the material is hotter, because heat reduces the stiffness of rock. They can mean the material contains partial melt, small amounts of liquid rock interspersed through solid matrix, because melt dramatically slows seismic waves. Or they can mean the material is compositionally different, made of different minerals than what the model assumes. The thermal anomaly provides one explanation for the slow velocities. If the rock is hotter than predicted, it should transmit seismic waves more slowly. That is consistent and expected. But the magnitude of the velocity reduction in the anomalous zone is larger than the temperature anomaly alone can fully explain. If you calculate how much the elevated temperature should slow the waves, you get a predicted velocity that is still faster than what is actually observed. There is a gap. Something beyond the elevated temperature is also slowing the waves. Partial melt is one candidate for filling that gap. If even a few % of the rock in those zones is liquid, the seismic velocities would drop substantially. Partial melt in the deep lunar interior is consistent with the hypothesis of ongoing geothermal activity. It would imply that there are pockets of molten rock existing today beneath the moon's surface, at depths far greater than any volcanic system could realistically tap, but present nonetheless. The existence of deep partial melt in the moon would be scientifically extraordinary. It would require that the thermal budget of the lunar interior is substantially larger than current estimates. It would have implications for the moon's future geological history. It would suggest that the deep lunar interior is not frozen solid, as assumed, but is still a complex, partially molten zone in which materials are slowly moving and differentiating. And yet the data pointing toward it is not imagined. The velocity gap is real. The researchers who have reported it have done so carefully, with full awareness of its implications, with multiple cross-checks against possible instrumental artifacts and analytical errors. The velocity gap is in the data. What the data does not contain is a definitive identification of the material filling that gap. Partial melt is one candidate. Unusual mineral assemblages are another. A material with an anomalously low seismic velocity relative to its density, which would be physically unusual but not physically impossible, is a third. The constraints on which of these is correct require the kind of data that only closer, more sensitive measurements can provide. This is where the intersection of science and mission planning becomes concrete. The questions raised by the anomaly data have specific answers that require specific instruments in specific locations. A seismic network distributed across the lunar surface, rather than clustered in one hemisphere, would resolve the three-dimensional structure of the anomalous zones far better than anything currently available. A deep heat flow probe, designed to measure temperature at depths far greater than surface instruments can reach, would directly quantify the thermal excess and help distinguish between radioactive heating and other heat sources. A magnetometer array placed in the anomalous regions would map the magnetic structure with enough resolution to distinguish between fossil magnetization and active generation. None of these instruments are currently on the Moon. Some are planned for future missions within the Artemis architecture. But the missions are in various stages of planning and funding, and the specific instrument complement needed to address the subsurface anomaly. Questions is not yet guaranteed to fly. This is a familiar frustration in planetary science. The questions are defined. The instruments to answer them are designed in principle. The physics is understood. The path from anomalous data to clear answer runs directly through a set of missions that have not yet launched. And the pace of planetary science is governed not by the urgency of the scientific questions, but by the practicalities of budget cycles and launch windows and organizational priorities that have nothing to do with the data. The scientific community has made this case to NASA and to international partners with increasing specificity in recent years. The subsurface science case for enhanced Moon exploration has been written into multiple strategic planning documents. The most recent decadal survey, the 10-year priority-setting exercise that the planetary science community undertakes to guide NASA's mission selection, specifically highlighted the Moon's interior structure as a high-priority research area. The language in that document was careful and measured, as it always is in documents of that kind, but the priority was unambiguous. Priority in a planning document does not guarantee a mission, but it is a step in the process that matters, and the presence of that priority, combined with the new data that makes the scientific case more urgent, has shifted the internal conversation within the lunar science community in ways that are beginning to have practical effects. Let me talk about the broader geopolitical context of all of this, because that context is shaping the pace and the direction of lunar exploration in ways that matter for how quickly the scientific questions might get answered. The Moon is experiencing a level of attention from space agencies around the world that it has not seen since the original space race. Multiple countries have active lunar programs at various stages. Some have already successfully landed missions. Others are planning landings within this decade. The motivations range from pure science to resource assessment, to national prestige, to the desire to establish presence on a body that several governments have explicitly identified as strategically significant. This crowded environment has implications for the pace of scientific discovery, because more missions mean more data. Instruments from different agencies with different scientific priorities, covering different regions of the Moon, will collectively build a picture of the lunar interior that no single agency's program would produce alone. But the geopolitical environment also creates complications. Space science has historically been one of the more cooperative areas of international relations. The norms of open data sharing and collaborative analysis have served the scientific community well for decades. But those norms are under pressure. Some nations conducting lunar exploration are not operating under the same data-sharing frameworks that have governed most of the science era of space exploration. The question of whether the combined global effort to understand the Moon will function as a coordinated scientific enterprise or as a series of parallel and partially overlapping national programs with limited data integration is genuinely open. For the specific question of the subsurface anomalies, this matters because the best scientific analysis would pool all available data from all missions measuring relevant parameters. The more instruments covering the relevant regions from independent missions, the tighter the constraints on what the anomaly actually is. If that data pooling does not happen, if different national programs are measuring the same zones but not sharing the results fully, the scientific community's ability to close the open questions is reduced accordingly. The current trajectory is mixed. Some international cooperation on lunar science is strong and active. Other relationships, particularly between the major space powers, are increasingly strained for reasons that have nothing to do with science. The lunar scientific community is navigating that terrain carefully, trying to maintain the norms of openness while operating in an environment where not everyone shares those norms. There is a scenario in which the anomaly question is answered faster than expected because of this international competition, because multiple independent missions land in or near the anomalous regions within a short window of years, and collectively produce enough data to resolve the questions currently left open. Competitive pressure sometimes drives scientific progress faster than cooperative pressure does. The original space race, whatever its political pathologies, was extraordinarily productive for space science. There is another scenario in which the competition fragments the scientific effort and delays a coherent answer, because the organizations with the most relevant data do not share it fully, and the partial pictures produced by individual missions cannot be meaningfully assembled into a complete image. Nobody knows which scenario will prevail. The outcome depends on decisions that have not yet been made by organizations whose priorities are not purely scientific. That is just the reality of how large-scale space science works. What is not in doubt is that the Moon is going to get a great deal of scientific attention in the coming decades, more than at any point since the Apollo era, and that the subsurface questions are going to be among the driving scientific questions for that attention. The trajectory toward an answer is real, even if the pace is uncertain. I want to come back to something I mentioned early in this story and spend more time with it, because I think it contains the most important insight in everything we have covered. The Moon is not the only body in the solar system showing signs of unexpected interior activity, and the lunar findings do not exist in isolation from a broader pattern of surprises that planetary science has been accumulating for the last 2 decades. When you put them all together, they point towards something that is beginning to look less like a series of individual anomalies and more like a systematic error in how we have been thinking about planetary interiors. Consider Enceladus, the small moon of Saturn. At roughly 500 kilometers across, it is tiny by any planetary standard, far smaller than our Moon, far more distant from the heat of the Sun. By every model we had for how small icy moons behave, it should be frozen solid throughout, geologically inert, essentially a large ice ball drifting in Saturn's outer system. Instead, Enceladus has a liquid ocean beneath its icy surface. It has active geysers shooting plumes of water and organic chemicals and silica particles into space from cracks at its south pole. The tidal forces exerted by Saturn are part of the explanation, but the energy budget required to maintain a liquid ocean and drive active geysers in a body that's small, that far from the Sun, is larger than simple tidal models predicted before the data forced a revision. Something in the interior of Enceladus is generating more heat than it should be able to generate. The revised models involve more efficient tidal dissipation within the icy interior than was previously thought possible, but getting those models to match the observed activity required multiple rounds of adjustment. Consider Europa, the larger Jovian moon whose subsurface ocean has been known for longer and studied more intensively. The tidal forces exerted by Jupiter on Europa are enormous, and they provide a clear mechanism for interior heating. But the details of how that heating is distributed through Europa's interior, how it drives the complex surface geology visible in orbital images, how it maintains an ocean estimated at perhaps 100 kilometers deep in a moon smaller than our own, still involve significant uncertainties in the models. The simple version of the tidal heating story is not sufficient. The interior of Europa is doing things that require more sophisticated models to explain. Consider Titan, Saturn's largest moon. Titan has a thick nitrogen atmosphere, hydrocarbon lakes and seas on its surface, a complex organic chemistry that has been called the richest laboratory for prebiotic chemistry in the solar system. It also has evidence of an interior structure that does not fit neatly into any single model. Some data suggests a subsurface liquid water ocean, which would make Titan an ocean world despite its frozen surface appearance. Other data suggests more complex interior layering. The picture is genuinely uncertain. None of these worlds individually constitutes a challenge to the basic framework of planetary science, but collectively they represent a pattern. Small rocky and icy worlds across the solar system are repeatedly showing more internal activity, more complexity and more thermal energy than models developed before we could actually measure their interiors predicted. The direction of surprise is consistent. Things are more active than expected, not less. Our moon fits into that pattern. And if you step back far enough to see the pattern clearly, the specific anomaly beneath the moon's surface starts to look like one instance of a broader phenomenon that we are still in the early stages of understanding. The phenomenon is essentially this: the models we use to predict how quickly planetary bodies lose their internal energy, the timescales and mechanisms of planetary cooling, are systematically underestimating the longevity of geological activity in small and mid-sized worlds. The models are not wildly wrong. They capture the broad strokes. But in the details of what specific regions of specific worlds are doing, they are missing something. What are they missing? The honest answer is probably several things, which interact in ways that compound the error. They may be underestimating the concentration of heat-producing radioactive elements in lower mantles. They may be underestimating the efficiency of tidal heating in worlds that orbit massive neighbours. They may be underestimating the role of deep partial melt-in, insulating deeper interior heat from conducting away toward the surface. They may be missing some interior convection processes that redistribute heat in ways the simplified models do not capture. The combination of all of these possible corrections working together could plausibly explain most of the surprises without requiring any genuinely new physics. That is the scientific community's default assumption, and it is a reasonable one. But it is an assumption that has been made and has been partially wrong before, multiple times, in the history of planetary science. There is a concept in the philosophy of science that is relevant here, sometimes called the pessimistic meta-induction. The idea is that the history of science contains so many examples of successful scientific theories that were later shown to be wrong, or to be approximations of a deeper truth, that we should expect our current theories to also be wrong, or to be approximations in ways we cannot yet see. This is not a nihilistic argument. It is a statement about epistemic humility. Our best models are the best models we currently have. They will be replaced by better models. The question is not whether that replacement will happen, but what will prompt it. The anomalous readings from the lunar interior are the kind of data that sometimes prompts model replacement. Not necessarily. The conservative resolution may be entirely correct, but the readings are in the right territory, the territory where the existing model's predictions and the observations disagree by enough that something has to give, to be candidates for the kind of data that eventually drives a theoretical revision. I want to say something about timing, because it matters for how we should think about the significance of what is happening right now. We are at an unusual moment in the history of lunar science. The combination of factors that has brought the subsurface anomaly to the current level of scientific attention will not repeat in the same way. The development of sensitive enough instruments to detect the anomaly, the placement of those instruments on the far side of the Moon, the availability of modern computational tools to reanalyze the Apollo data, the series of orbital missions that produce thermal and magnetic maps precise enough to show the regional correlations. Any one of those elements alone would not have been sufficient. All of them together, arriving within a span of roughly 2 decades, produce the convergence of evidence that makes the anomaly scientifically undeniable. That convergence took a long time to build. The next convergence, the one that will either confirm the anomaly's significance or explain it away with high confidence, requires instruments that are planned but not yet deployed, missions that are funded but not yet launched, data that has not yet been collected. The gap between the two convergences is likely measured in years to perhaps a decade and a half, depending on how quickly the relevant missions actually launch and operate. During that gap, the anomaly will sit in the scientific literature as an open question. Papers will be published on various aspects of it. Conference sessions will be devoted to competing hypotheses. The ongoing analysis of existing data will progressively sharpen the constraints, narrowing the space of possible explanations even without new instruments. The picture will get clearer, but it will not get fully clear until the next generation of in situ measurements arrives. This is worth understanding because it sets the context for what comes next. The story of the lunar subsurface anomaly is not a story that is about to end. It is a story that is about to get more detailed, more contested and more consequential over the coming years. The findings that have been quietly gathered and quietly analysed are going to become public, in stages, as papers complete review, and researchers conclude that their analysis has reached a point where publication is warranted. That process has already begun. It will continue. And as each new piece is published, the community conversation will sharpen. The public conversation tends to crystallize around breakthrough moments, single papers or press conferences or announcements that simplify a complex ongoing scientific story into a headline. That kind of crystallization is probably coming for the lunar subsurface. At some point, the accumulated weight of evidence will be sufficient to justify a statement that is clear enough for public communication. When that statement arrives, it will either say that the anomalies have been explained within existing frameworks, or that they require revision of those frameworks. Either conclusion will be presented as if it arrived all at once, but it will actually be the accumulation of years of work that was happening quietly while the public was not watching. I have spent a lot of time in this story on the scientific details, because the scientific details are where the real story lives. But I want to end somewhere different. The moon, as an object of human attention, carries a quality that is almost impossible to fully articulate, but is deeply felt by anyone who has stood outside on a clear night and looked up at it. Its familiarity, its permanence within human experience, the fact that everyone alive today, and everyone who ever lived, has looked at the same moon. It does not change within a human lifetime. It does not change within human history. For all practical purposes, from the point of view of an individual human life or even a long human civilization, the moon is simply there, always the same, always in its predictable cycle. That perceived permanence is part of why the news that the moon's interior is stranger than we thought lands with a particular kind of weight. It is not just a scientific finding, it is a small revision to the background assumptions of human existence. The thing that you thought you knew completely, the object that has been overhead for every human generation, in every culture, in every part of the world, is not quite what you thought it was. There is something in the lunar regolith, in the deep dark below the footprints that 12 human beings left in the dust of the near side that we do not yet understand. Something that has been there since before those astronauts were born, since before the program that sent them there was conceived, since before the civilization that built the rockets existed, since before the species that built the civilization evolved. It is waiting. Not impatiently, because geological time has no impatience in it, but waiting in the sense that it is there, and that it will yield its nature to instruments precise enough to measure it when those instruments arrive. The instruments will arrive. They are being designed. They are being built in some cases. The missions that will carry them are being planned. The science that will interpret the data they return is being written, right now, in papers that build on the existing anomaly findings and extend the models and narrow the range of possible explanations. We are not at the end of this story. We are somewhere in the middle of a very long chapter, a chapter that began the moment the Apollo seismometers first picked up the ghostly echoes of moonquakes in the early 1970s, that continued through every mission and every reanalysis and every unexplained reading since. And that is currently in a phase of productive uncertainty, the kind of uncertainty that science generates before a resolution arrives that changes everything. The change may be modest, a better model of lunar interior composition, a revised timeline for the cessation of volcanic activity, a deeper appreciation for how long small worlds can remain geologically interesting. Those outcomes are scientifically valuable and would improve our understanding of the solar system in meaningful ways. Or the change may be larger, an interior that does not fit any existing model, requiring a genuinely new framework, a realization that the moon's thermal and magnetic history is fundamentally different from what 5 decades of study had suggested, a discovery that forces the planetary science community to go back to the beginning of several long-held assumptions and rebuild them with better data. That outcome is also possible, and the data, read honestly, does not let you rule it out. Either way, the moon is not finished with us yet, and we are not finished with the moon. The 6 months of institutional quiet that opened this story will not last forever. Science is not always loud, it is rarely fast, but it moves, steadily and incrementally, and sometimes with sudden lurches forward, and it does not stop. The data that was collected is real. The researchers analysing it are real. The questions they are working to answer are some of the most genuinely open questions in planetary science. And when the answers arrive, they will matter, not in an abstract way, not in the way that discoveries about distant galaxies or exotic particles matter, as expansions of knowledge that affect everyday life only through the slowest and most indirect channels, in a particular way, in the way that things matter when they involve the closest world beyond our own. The world that has been above every human head for every night since the first human looked up. What is beneath the surface of the moon is a question that belongs to all of us. It has been asked, implicitly, by everyone who ever stood in the dark and looked up. The scientific community is in the process of answering it, carefully and responsibly and slowly, in the way that genuine answers to genuine questions are earned. Whatever the answer is, it was worth asking, and it will be worth knowing.